Welcome. In this demonstration, we're going to clean up some data and see if it is normally distributed. So what I have here in front of us is some actual data from a grade book. And you can see that there are chapters across the top and some other assignments in there. And what I want to illustrate with this is that often real data is messy and you have to make some decisions. And those decisions are going to be based on the type of question that you want to answer. So I want to know if the total score from the assignments that are due at this point is normally distributed. And so I'm going to make various decisions to help me get to that point. Now, these decisions are not necessarily right or wrong. You could make different decisions if you had a different question that you were trying to answer. And this is the type of thing that you will face all the time when you're working with data. What do we do with this missing data? What do we do with this data that's out of range? That type of thing. So in this data, you can see that we have missing values. We have values that are starred. And I can tell you that at this point where the data was collected, that students should have completed up through chapter 2, and yet we can see some students have gone beyond that. So here are the decisions I'm making about those things. I don't need any of the chapters that are not due. I'm only curious about the normal distribution of the assignments that are due at this point. So, or at the point that the data was collected. And so that was at the end of chapter 2. So I've deleted chapters 3 through 5. In addition, there's some preliminary assignments here that I don't need either because those actually don't contribute points to the overall grade. And so we'll delete those. So now I'm left with the chapters that I am concerned about. However, I have missing values and I have values with a star or asterisk. Now the value with a star or asterisk means that it was a late assignment. So what I'm going to do for those is simply remove the asterisk so that it is a number that Excel can process and do calculations on. But before I do that, I'm going to get rid of any record, so any row, student record, that is missing values. Because the question I want to answer is, for those students who have done all of their assignments, what is the total score? Is it normally distributed or not? And so if a student has not done all of the assignments, I'm going to delete that student's record, so we can delete these. And we can delete this one and this one. Oops, the whole row. Notice that I'm doing this manually and I've already missed one record here that should have been deleted, and manual operations are prone to error. Now I could use a formula to figure out which columns have blanks in them and which rows have blanks in them, but this data set is small enough that I'm going to stick with the manual operation. And it looks like I'm left with 36 records to work with, and now I need to convert those values that really a text into a value, and I'm simply going to remove the star. Okay, looks like my data is clean. What I want to do now is a total row here. So this is going to equal the sum of A2 to F2 to give me the total points. Now I'm concerned about the total points from the standpoint of this is the data that I'm actually analyzing. I needed all of this chapter content data to figure that out, but now I don't need it. However, if I simply delete these columns, I will lose my total because it's a formula based on those columns. So what I have to do is highlight this and copy it and paste it as the number. So you can see this is a formula, but this is the actual number. So now I can delete all of these. Let me show you what happens if I were to just delete those. Notice that the formula in there cannot be calculated because the references are gone. So I don't need this. So this is my total. And I want to sort this. So data, and I want to sort it in ascending order. So the lowest number is first and the highest number is last. Now, I know from where the students are at in this particular class that the possible points at this stage, at the end of Chapter 2, was 280 points. What I'm going to do now is I'm going to normalize the grade on a scale of 100. So could leave it as is, but it's a little easier to think about a grade that's a 95, you know it's 95%, than it is to think about a grade that's, say, 243, 244. What percentage is that? So this is simply a percentage, so it's going to be A2 divided by F1, and I'm going to copy this down so I'm using absolute references, and I'm going to multiply that by 100 because of course when we do the percentage it's a decimal place and I want the whole numbers. And typically with grades we don't need that many decimal places, so we'll simply reduce the number of decimal places. Let's just say 1 decimal place and copy this down. So now I have the same data, but it's normalized on a 100 scale, 0 to 100. Now the next thing I need is a rank z-score, so a rank-based z-score. In one of my previous demonstrations, I've shown how to get this, and I'll be building all of it in one cell here, one column. But it can be built separately if you need to do that. So the idea behind this is I'm going to standardize this or make a standard score out of it, a z-score, that is in standard deviation. And to do that, the formula that I need is I need to have a rank-based quantile, and then I need to convert that to the rank-based z-score, or to the z-score. It's already rank-based at that point. We're going to use norm.s.invert for our function here. And we need a probability. So this is where the rank and the quantile come into play here to give us this rank-based z-score. So I need the row, so row minus 1, because we're in row number 2, but it needs to be item 1. And so we're going to put that in parentheses. And I need to subtract 0.5 because I'm using that Hayes method for doing my quantile. And then I'm going to divide all of that by my count, and that is B2 to B, I think it was 36. I can correct that if wrong. Ending quotation. And what have I done wrong here? Okay, so, oh, right here. So I typed in row, but I don't actually have a function. To get the function, I need the opening and closing brackets there, parentheses, and it will recognize that as a function. And so there we go, we have our function. Now I'm going to reduce this down to display, let's go for 2 decimal points on this one. Now the other thing that I need to fix here is I notice I did not use an absolute reference to these. So I want an absolute reference because when I copy it down, then it'll copy properly and have the proper count. All right, now I can copy this down and get the rank-based z-score for all of my totals. Now the next thing I'm going to do is insert descriptive statistics with the analysis tool pack. And I am looking for this whole normalized column here. This is my scores from 0 to 100, or on the scale of 0 to 100. And let's put it in, let's just go with E3. And I want summary statistics. And I've forgotten to click my labels in the first row. So there you go, got a nice notice for that. Okay, so here we go. The mean is 77.84. The median is 78.19. Very close. That's a good sign. As I go down here, kurtosis and skewness are quite small. 0.28 for kurtosis and 0.6, a negative 0.6 for skewness. And recall that 0.5 is kind of an easy threshold to use. If the absolute value of your skewness is 0.5 or below, then it's a pretty good chance that it's normally distributed. We're just outside that, so let's see what we can determine using a QQ plot. Okay, you can see from the QQ plot that I do have some variation in this, a little bit of a rise here, some bubbles here, bumps if you will, as well as both ends trailing off below this trend line. So the next thing I want to do is insert a histogram. So I want a histogram on my normalized data, that scale of 0 to 100. And so I'm going to insert that. Let's see what it gives me for recommended. There we go. There's a histogram. Now, that's what I want to use, but I also want to show you that if it doesn't give you that for a recommended chart, you can come over here, and this is the drop down for inserting a histogram. So it gives you the same thing. So this is our histogram. And again, I've inserted a histogram rather than using the data analysis tool pack because I'm not too concerned about the spreads here. With inserting a histogram, it selects those the bin width itself. Excel assigns those, and so I'm not really even concerned about those. I'm more concerned about the look of the shape, if you will. It has a normal distribution look. There's more here than there are here, so we're a little light on this tail here. So again, we're close. We're close with the skewness. We're close with the QQ plot. We're close with the histogram. So remember that all real data is not perfectly normally distributed. What we're trying to determine is it close enough so that we can treat it as normally distributed data. And this is looking pretty close. Now I have one more test that I want to do, and this test is called a D'Agostino-Pearson omnibus test. It's one of the many mathematical tests that you can run on a data set and determine or help to determine if it's normally distributed. So I have some items that we need to fill in here. So I'm going to put those here. So we're going to look at the skewness, which we can just pull from the descriptive statistics. We're going to look at the standard error of skewness, and then we're going to do a standard score for skewness, and we're going to do that for kurtosis. And then this DP is the actual D'Agostino-Pearson omnibus test, and we'll calculate that as well. So I can say that we're going to work with a significance level of 0.05. So that's a choice that we're making here. And that the skewness is equal to this value up here. And that my kurtosis is equal to this value up here. Now the question is, how do I calculate the standard error of skewness and the standard error of kurtosis? So glad you asked. So I want to show you a couple of formulas for this. So here's the standard error for skewness. So n being the number of samples that I have, I believe it's 35 in this case, our count. So we're going to do 6 times n and then multiply that by n minus 1 and then divide that by n minus 2 times n plus 1 times n plus 3 and take the square root of all of that. Now, you don't have to understand the reasons behind this to know that that's the way we calculate the standard error for skewness. So let's get to calculating. So this is another formula that you could build kind of one step at a time if you want, because there are a lot of steps to it. But let's just jump in and do it. Square root, here we go. That's the one we want. And the very first thing we want is that 6 times my n. So what is my n? The count, we can see the count is right here in F17. So we're going to do 6 times F17, and all of that gets multiplied by F17 minus 1. Now I'm looking at the formula here outside the screen, and you'll need to look at the formula when you build this as well. I don't have this memorized. And I'm going to divide that by the quantity of F17 minus 2 times F17 plus 1. And remember, F17 is our count, times F17 plus 3. It looks like a pretty clean calculation. So there you go. Looks like it works. So again, I've implemented this formula for the standard error for skewness. Now I need a standard error for ketosis. And we're doing that second because, in part, well, largely because of, it is based on the standard error of skewness. So here's the standard error of ketosis. I take 2 times the standard error of skewness and then multiply that by the square root of n, our count, squared minus 1, divided by n minus 3 times n plus 5. Again, you don't have to understand all the reasons behind this. At many levels, we trust the mathematicians who create this. In this case, D'Agostino and Pearson, combining to give us the D'Agostino-Pearson omnibus test, not the standard error of ketosis and standard error of skewness. Those have been around much longer. Okay, so let's type this formula in. And again, I'm looking at it elsewhere off screen. I don't have this memorized. So we're going to equal 2 times, and this is F21, which is our standard error of skewness, times the square root of, what do we have here? We have our count squared. So I need to do, oops, I need that symbol. I need the count squared minus 1, and all of that divided by the sum of my count minus 3 times my count plus 5. And looks like a good formula. Let's see what we've got. Yes, we've done it. We've calculated the standard error of skewness and the standard error of ketosis as well. So now we need a standard score for these. So remember, a standard score is, it puts it in the measurement of standard deviation. And so that is pretty straightforward. To get the standard score, we're simply dividing our skewness equals F20 divided by that error, and this puts it in the standard deviation units of measurement. And we'll do the same here, so equals F24 divided by F25. Now both of these are within the range of what we would hope to see if this is normally distributed. So roughly speaking, we're looking at an absolute value of 2 or less for both the standard score for skewness and the standard score for ketosis to say that this has the possibility of being normally distributed. So now we can calculate the D'Agostino-Pearson omnibus test. Now that test is simply the square of our standard score for skewness plus the square of our standard score for ketosis. So we have equals F22, and we'll square that. And then to that, we're going to add F26, and we'll square that. So now we have the D'Agostino-Pearson omnibus test. We have a result from that. And to determine whether that result tells us that it's likely to be normally distributed or not, we need to calculate a p-value. And the way we calculate the p-value is with the formula chi-squared distribution, and this is a right-tailed distribution that we're using here. And so the x is our dp results, so F28, and it's based on 2 degrees of freedom. And so it is the p-value. Now that's more than our significance level of 0.05. So based on the D'Agostino-Pearson omnibus test, this is normally distributed data. And so notice that we can look at many things to help us determine if this is normally distributed, because real data always has some non-normalness to it in the distribution. So we can look at the skewness. Is it absolute value of 0.5 or less? A little bit over here. We can look at the QQ plot. It's close, but some variation. We can look at the histogram. It's close, but some variation. We can look at the standard score of skewness and the standard score of ketosis, and they're below that absolute value of 2, so a good chance it's normally distributed. And we can look at that p-value from the D'Agostino-Pearson omnibus test, and it is more than our significance level here. So we would say, yeah, this is normally distributed. I will treat it as normally distributed data. So there you go. Now it's your turn to try.